So hello to this workshop on data and models interoperability for artificial intelligence systems in manufacturing, which is organized by the AI for Manufacturing cluster, the cluster of ICT 38 European projects on artificial intelligence in manufacturing. This is the fifth in a series of workshops that we have organized in the cluster for over a year. Previous topics were on explainable artificial intelligence, on the legal issues of artificial intelligence in manufacturing, and also in topics relating to Industry 5.0 and human-centered manufacturing. So today's workshop will unleash the potential, will present how we can unleash the potential of interoperability for AI systems in manufacturing and what this potential can deliver in the shop floor. We have four excellent speakers. This is John Soldatos from Star Project and net company Intrasoft. And without any further ado, I would like to give the floor to our first speaker, a class from Flanders Make and Assistant Project class. Please feel free to introduce yourself and your talk, and have 20 minutes to talk about manufacturing data information and how to create actionable knowledge out of them. Class, the floor is yours. Please introduce yourself and proceed with your talk. Thank you very much.
Good morning, everybody. Let's see. Can you hear me?
Slides, class. Yes, we can see your slides and we can hear you.
Oh, perfect. Good. Then I'll go ahead. My name is not Bart, but my name is Klaas. And I'm volunteering here to take over the presentation, for whom all the credits should go to my colleague Bart Meijers. And I'm going to present you indeed some of the work that we have been doing and we are currently doing in the H2020 Assistant project. I have quite some slides included in the slide set. Some of them I will go over quickly, especially indeed since we will make the slides available in a PDF format, and it might be useful to go over some of them in more detail a little bit later. Very shortly, Flanders Make is a Belgian, a Flanders RTO, which is focusing on performing innovation activities, research and innovation activities for Flemish, but also for European manufacturing companies. We're in Flanders, we're called a strategic research center, meaning that we have activities at all Flemish universities, and we also have some custom labs apart from the universities, resulting in 750 plus researchers spread over Flanders. I will skip this slide. I also will skip the background on Bart that you can look at later. And so today I will present you some of our work in the Assistant project. Also here I will go quickly over it. As John mentioned, this is not the first workshop. So to avoid too much repetition, Assistant is indeed one of the ICT 38 projects, which is called Learning and Robust Decision Support for Agile Manufacturing Environments. And so the goal of Assistant is to be able to provide this decision support for multiple activities that are being carried out in the complete manufacturing process, going from process planning, which typically happens 6 months in periods about 6 months before the actual manufacturing starts, towards real-time decision support real-time decision support on the shop floor, involving decisions on how to tune particular machines, how to replan, or how to, and this is what my talk will be about today, for instance, how to ensure quality, where one decision could be, when do I need to perform quality assurance measurements and when not. I also have a slide with the consortium in mind. Assistant consists of some research partners and 3 industrial cases. The 3 industrial cases coming from companies Atlas Copco in Belgium, Stellantis in France, and Siemens Energy in Germany. And today I will focus on an industrial case of Atlas Copco in Flanders. So to go a little bit more in detail on the case, I like to give some presentations which are somewhat example driven. This is one of the cases that we're performing research on in the project, and it's about the manufacturing process of a housing of a compressor system. So Atlas Copco is a compressor manufacturer, and one of the steps in such a manufacturing process is a CNC process that can turn an ugly mold into a very accurately milled and drilled housing for a compressor, in which in a later stage then 2 rotors are inserted. So this process consists of drilling some holes, milling some surfaces, but as tolerances are very important, quality is measured by doing some measurements. Currently, before the project started, Atlas Copco was for every product doing some quality assurance using the internal probe of the CNC machine. Having an operator after each part came out of the CNC machine, perform some manual measurements for the critical dimensions using an e-caliper. And thirdly, for some parts, typically 1 out of 10, detailed measurements were carried out on a coordinate measuring machine. Of course, as you can see, these are quite a number of measurements due to the fact that this quality is really important. But the question which Atlas Copco asks themselves in this project is, okay, now can we not come up with a decision support system, or a digital twin, if you like, that can help us deciding when we need to measure more and when we can measure less? And so this is the decision support for this particular case, of course, with the end goal to reduce the number of measurements, but keeping the same quality. And how can we do that? Of course, via an AI system. And for this AI system, we, on the one hand, have all this quality measurement information, but secondly, we have all of the measurements which are recorded from the CNC machine, such as, for instance, and I will come back to that later in the presentation, temperatures of the cooling liquid, which are measured and which are also stored in online databases in a data lake. And the goal is to combine these with expert knowledge and AI techniques in order to be able to reach that goal. As I also mentioned before, such a decision support materializes via a digital twin. In the remainder of my presentation, I will call this a streaming digital twin. A streaming digital twin which observes live information, in this case from the CNC machine, performs some streaming analytics, and then, for instance, uses a dashboard to alert an operator when more measurements are needed in order to ensure the quality. Now, the question is, how do we get there? In a very simple world, you then just say, okay, but it's easy. We collect all of this data, we perform some deep learning, we have an algorithm, we deploy that algorithm somewhere on the edge, and it's solved. In reality, this is not the case because such a deep learning model, even if it would work well, it's not explainable, and it ends up with problems being accepted by the operators. And secondly, typically in a manufacturing environment, especially in a high mix, low volume manufacturing environment, there is not too much data, and there's especially also not too much data on failures, which results typically in models that are not usable. And this is a path that at least Atlas Copco tried to take before, but didn't work. Now, then the question is, how can we solve this? And why do we need a knowledge graph in order to be able to solve that process? In the remainder of the topic, I'm going to show you that it's not just about the data, but it's also about information, and it's about the knowledge which is available in several places in the company, and as such, interoperability is also needed in order to be able to combine the data, the information, and the knowledge from several people in this manufacturing floor in order to be able to finally be able to implement such a decision support system. Okay, so as I mentioned before, the end goal is to create this digital twin that can provide decision support. Now the question is, how do we get there? And we get there via the help of some data scientists. What does a data scientist typically do? He goes through a complete process, and in that process he starts from exploring data or information, extracting information from the data, analyze it, look at correlations, calculate some features, and then finally creating some insights. And so basically, if you look at it from an architecture point of view, and to come up with an interoperable architecture, you don't only have the streaming digital twin, but you have a complete platform consisting of a data lake that captures, on the one hand, information from the OT devices on the factory floor, but where we argue that this is not sufficient and that you need to combine it with, for instance, design information, expert knowledge, but also, for instance, simulation models. And all of these are being or can be integrated into a manufacturing knowledge graph whose goal it is to make the life of the data scientist easier. And so in the remainder of the presentation, I'm going to go over, let's say, three main functions of the knowledge graph, which allow you to get some value out of your data. So these three main functions are: one, it allows for the data scientist to explore the data, thereby linking heterogeneous data via providing an abstraction layer. Secondly, by including and modeling all kinds of knowledge into the knowledge graph from different subject matter experts, making all of that knowledge interoperable such that it can be used by the data scientist. And I will detail some of the knowledge that we incorporate in the knowledge graph in the assistant project. And finally, allowing the data scientists to generate some actionable insights. So the remainder of this presentation, I'm not going to give too much theory, but I'm going to try to give you an example-driven story to make it a little bit tangible, providing an overview, a high-level overview of our vision and the interoperability of the knowledge graphs in manufacturing. There are some caveats, of course. The slides are somewhat oversimplified, and not everything that we present here is already finished work. Some of it is also ongoing. Good. Coming back to this function one, exploring and understanding the data. as they say, data is the new oil or data is the new gold. So they say in practice, when a data scientist tries to solve the problem which I sketched earlier, one of the questions that, for instance, he is asked, what are now these influence factors that influence the test results of the quality assurance step, and how can we predict them better? And in order to be able to answer that question, one of the things that he wants data for is, for instance, an answer to the question, now give me an overview, give me all of the data of all products that failed quality assurance tests. And since I have heard that temperature data might have an influence, the temperature of the curing process step might have an influence on this quality, I want to have access to this temperature data. If you now look in practice, where is this data stored in the data lake? Well, basically all over the place. The product data is stored in an ERP database. The quality information is stored in a separate relational database with the quality assurance test results. The temperature data are typically time series data, which are stored in a time series database. And in order to link everything together, to know on which machine, on which CNC machine a particular part was processed at which time, we also need information from the manufacturing execution system. And so when the data scientist wants to gather this data, basically the reality is that 80% of his time he spent in understanding, preparing and retrieving the data. And so there we end up as a first function of this knowledge graph being making this data access interoperable and turning data into information via providing the data scientist a single access point, which is in this case the knowledge graph, to all of these different data sources. And then there are some different notions whether you store the data in the knowledge graph or you do not do it, which we call virtual knowledge graphs. But basically, this allows the data scientist to query a single access point via a query language. In this case, you see the example of a Sparkle query. Where this plain text query of a couple of slides ago is here formulated as a Sparkle query. So instead of talking SQL, I forgot the exact name of the query language of the Influx database, for instance, talking REST APIs, he can now access all of this information and the data which is put into a certain context via the knowledge graph. And we found out that this saves the data scientist a tremendous effort and a tremendous throughput and execution time. A second function of this knowledge graph is to be able to model knowledge. And without going too deep into detail today, I'm going to show three types of knowledge, manufacturing knowledge, which we incorporated in the knowledge graph in the assistant project, influence factors, executable models, and then probabilistic knowledge. First example of these influence factors, again, I have here the knowledge graph saying that I have this compressor housing, I have some process steps. These process steps are carried out on CNC machines. These CNC machines have their properties such as the machine bed temperature, and we also perform measurement steps on the compressor housing. And in one of these measurement steps, we measure the bore diameter. Now, some domain expert, some subject matter expert typically has some knowledge because he's maybe an operator and he thinks that there might be a relationship between bad quality and deviations in the machine bed temperature. Then one of the things that the data scientist typically has to do today is to query all of these subject matter experts in the company, which again takes a lot of time, where the approach that we propose here is that we incorporate such influence relationships via explicit relations in the knowledge graph, such that then the data scientist can query the knowledge graph for these influence relationships and can, for the various various relationships, indeed check whether this correlation in this case exists. And secondly, for instance, fit a model into this that can predict the quality of the bore diameter based on the machine bed temperature, and also incorporate this updated information in the knowledge graph. A second part of knowledge that we include in the knowledge graph is what is called here executable knowledge. And for instance, these are things where you say, okay, I don't need the direct data, but I need indirectly data. So I need to perform a calculation step on the data before I can actually perform a correlation step or train a model. And some examples are given here. We call this on-the-fly calculation, the on-the-fly calculation step of the knowledge graph. And there are three examples given here. For instance, maybe it's not the average temperature that we need, it's the maximum temperature. And then via a script calculation, we can provide this, but this should be transparent for the data scientist, and he can just query the max temperature in his Sparker query. For some aspects, we might have already trained an AI model in the past, and also that kind of calculations we can perform. Secondly, typically during the design, a lot of design models are made that perform some simulation, for instance, CFD simulation that can help us here. And also these CFD simulations that can, for instance, be accessed over REST. We can basically call them on the fly and use them in order to make the life of the data scientist easier. Then, given the fact that I see that it's already 5 to 11 and I'm at the end of my limited time, I'm going to go very quickly over this. One big aspect, of course, is to be able to sorry, it's my telephone. One aspect is to be able to also explicitly represent uncertainty into the knowledge graph, uncertainty from measuring, uncertainty from bad models, and also there we have, let's say, explicitly modeled this kind of uncertainties into the knowledge graph. Using all of these, you can generate insights in the knowledge graph, for instance, performing root cause analysis, looking for correlations. Secondly, you could use it to perform predictive analysis to be able to predict the end-of-line performance at any stage of the production process based on the available data. And the later you are, of course, then you should see that the uncertainty decreases. And so I rushed a little bit through the end, but so my main message of today is that the knowledge graph can help the data scientist in order to combine all of the data which is stored in several places and all of the knowledge which is stored at several places in a manufacturing organization in order to be able to reach actionable insights a lot faster from the data and knowledge which is in there. And so this was the last talk. In reality, it looks more like this. So this is an example visualization of the knowledge graph, still a simplified example, but where you can see that in reality, of course, there are a lot more properties and process steps involved, and where we use the knowledge graph in order to serve Atlas Copco. Good. I reached the end of my talk 1 minute late. Apologies for that.
Thank you, Klaas, for keeping the time and for the nice presentation. I would like to ask if there are any questions on Klaas before going to the next presentation. Are there any questions on how knowledge graphs are used to make data-driven intelligence?
Maybe Mari from Team AI, not a question, but just a remark. Klaas, I met Bart at the FRI event in June in Brussels, where I introduced our knowledge graph approach in the Team AI project. So this was more or less the trigger for the meeting today. And I definitely would suggest that we have a more stronger collaboration between Assistant and Team AI, because we are really going in the same direction. And I think the next presentation from our colleague from the University of Mannheim will clarify that issue further.
Yeah, that's great. And indeed, maybe we should also set up a bilateral meeting in order to go in a little bit more of technical detail.
My question, Klaas, if you could accept a question from me, and I would ask for a quick answer because for the sake of time, is the implementation side of those things? I mean, how do you really implement knowledge graphs? Do you use some, kind of semantic toolkit and semantic modeling approach? Because the concern here I have is that we've used this in past projects, and they are generally, slow in terms of processing and have high latency. So in an industrial environment, we usually want things which are very fast, low latency, and so on. So how do you deal with this? If you could give a quick answer, I would appreciate it.
Yeah, I'll try to give a quick answer, but it's indeed, it's a hot topic. It's an interesting topic. In one of my slides, you noticed that I gave a little bit of technical detail determining between, let's say, virtual knowledge graphs where the data remains in the data store, and I would call it normal knowledge graphs where the data is loaded into the knowledge graph. And so this is one trade-off mechanism that you have to make, doing the trade-off between having to load data too many times, but having faster performance if everything is directly into the knowledge graph. And then secondly, with respect to tooling, we, for instance, use a combination of Databricks and for the virtual knowledge graphs, the on-top environment. And we have indeed implemented some improvements in order to get this execution speed, let's say, par with what a data scientist is used to.
Okay, thank you, Klaas. So it's a key to have, if you want speed, you need to make sure that the graph is loaded in memory, right? And the reason is done there, not on disk.
Yes, and there are several tricks to reach it.
Yeah, okay, I can imagine. Thank you. That's a really very useful. If you have a paper and so on, feel free to share with us in the cluster. And let's move to the next talk. Thank you, Klaas, again to move to Frank. Teaming AI, please feel free to introduce yourself and go on with the presentation. Thank you.
Yes, so first of all, thank you for the introduction. So my name is Franz Krause. I'm from the University of Mannheim, but also from the Teaming AI project. So we are aiming at enabling human AI interaction in manufacturing. And today I want to talk about time awareness and knowledge graphs. And actually, my keyboard does not work, but now it works. Actually, this presentation is based on a paper of ours that we submitted to the Semantics conference of this year, which has also this exact same title. So there, it's pretty much the same, which is listed in the paper as well. So if you want to get into detail, you can read it as well. It's freely available. And we're also happy to share that it won the Best Paper Award this year. And I hope that I won't disappoint some of you, because I won't get too much into detail regarding manufacturing today, because the approach that we're facing is very general and it can be used in any dynamic domain which is meant to be encoded in knowledge graphs. But manufacturing is also a dynamic domain which can be encoded in knowledge graphs. And therefore, we use these results in teaming as well. Now, onto the first slide, I want to tell you why we wrote this paper. Now, most of you most probably know that there are some standard requirements if we want to integrate knowledge graphs into a domain, such as integrability and standardization, and therefore also interoperability by means of some standardized vocabulary which is used in this domain. But within the last few years, it became more and more obvious that we need some additional added values in downstream tasks, such as knowledge graph embeddings, graph-based learning, so graph neural networks, and also regarding the explainability of existing AI models. And you might have guessed it, all of these tasks are meant to be covered in teaming AI as well. Now, fortunately, there are already some works in this regard, but we found that most of them are, if not all of them, are done without consideration of time awareness for so-called static knowledge graphs. So static is handled as the opposite of time aware. And that's a problem for us because it's not just static. There are a lot of notions like temporality, dynamics, which are used totally interchangeably and in particular inconsistently, because there are a lot of aspects to time awareness. And we want to provide a generalized framework for that. Now, that's some information for now. So let me take one step back and start off with a very simplified, oversimplified example. And we want to get to know what a seal is. For this, we have invited 5 participants, and each of them is supposed to answer this question. Now, the first one would say that this cute-looking animal here is a seal. The next participant would say that this monstrosity here is a seal. And that's when the heated discussion starts. So everyone has another opinion on this topic. But what if I told them that all of them are right? Because the seal is a very broad species and all of these animals are seals. Now, this is cool and all, but you might ask yourselves now, what the hell is this guy talking about? But it becomes more and more obvious if we slightly change the question to what is a knowledge graph? And again, we ask 4 participants to answer this question. The first one is a software engineer, and she has looked into the term knowledge graph 10 minutes ago. So she can give me a list of knowledge graph frameworks, which can be used to implement knowledge graphs in her domain. But as you might have guessed, these are frameworks. And initially we start off with an empty graph, but still we can define queries for this graph and we can add information to this graph. So are we not supposed to, think of empty graphs as knowledge graphs as well? It's not so easy to answer, but let's just keep that in mind, because the next regarding the next participant, we face a very similar problem. He's a mechanical engineer, and according to his opinion, this structure here is a knowledge graph, but it's very obvious that it's just some tabular data from an Excel file or CSV file, and each sensor value represents a row in some CSV sheet, for example. But still, we have some nodes, we have edges, so we have the atomic components of a knowledge graph. So maybe we need to consider this as a knowledge graph as well, even though most knowledge engineers might argue that we're missing interconnectedness of concepts here. The third participant, on the other hand, is just a football fan, and he made a sketch of his 2 favorite footballers, Cristiano Ronaldo and Lionel Messi. And pretty much no one would argue that this is a knowledge graph, because we have edges to some literal values like the birth year or the height, but we also have contextual information like the teams the players played for or the tournaments that were won by these teams. So that's pretty much a knowledge graph, isn't it? Yeah, so the last participant states it is a knowledge graph, but the encoded information is not sufficient for some downstream tasks. So she extended this knowledge graph by a little bit. And to understand this, we take a closer look into it. And what she's done is that she basically just added some temporal metadata to the edges in the graph. Like, for example, Lionel Messi playing for FC Barcelona from 2005 to 2021, and Cristiano Ronaldo playing for Real Madrid from 2009 to 2018. Now, this additional information is useful for certain downstream questions, like, for example, how often has Messi scored matches against Ronaldo? Because with this additional information, we know that they played against each other in the same league for at least 9 years. And it's better to have this information than not to have it. Now, there are also other downstream questions for which it's not so obvious why temporal metadata is useful for it. For example, does Cristiano Ronaldo like British food? Now, with the current graph, without any additional metadata, we wouldn't really be able to solve this answer. And we're still not able to solve this answer with the temporal metadata. But as you can see, the previously unique edge, Cristiano Ronaldo playing for Manchester United, became 2 edges because he played or plays for them twice. The first time from 2003 to 2009, and he's still playing for them until now. And so we know he played for them twice, and we can at least infer that he doesn't dislike British food so much that he wouldn't return to England for playing for Manchester United. So we have 2 different representations of a knowledge graph, and we want to have some generalized, standardized setting. So we get into staticness again, and we define static edges as triple edges, as most of you know them. So we have a head node, a relation, and some tail node or tail literal. And the set of such edges is a static knowledge graph. So we can't expect any additional information. We're just working with triples. Now, most knowledge graphs are based on some schemas, some taxonomies, and especially ontologies. And ontologies which are defined for the logical inference of static edges are called static ontologies. So they are designed to handle static data. Now we also introduce the notion of induction. So a data model D induces a static knowledge graph if the static knowledge graph can be derived directly from D. By this, we also want to allow data sources which are not per se knowledge graphs to be applicable to graph-based downstream applications. And to do this, it's your task to constrain the data model D to suit your needs. Now, regarding all of these notions of static and so on, we get back to our example. Now, a static graph is just a graph consisting of triples. So we don't have any additional metadata, and it becomes non-static as soon as we can expect at least one additional metadata for an edge. But we want to talk about time awareness. And even though we are only looking at time-related metadata here, in non-static graphs, we can also add information which is not time-related, like me being the creator of the edge or the fact that Portugal won the European Championship in 2016. So we need to define temporality or time awareness. And we always do this with respect to some ordered set of timestamps T, which can be years, months, days, or timestamps in general. But without loss of generality, we just assume them to be either discrete or continuous. So we assume them to be the natural numbers or the real numbers. And by means of a fitting mapping, we can, well, backpropagate our original timestamps. Further, we introduce the closure of our timestamp set, which is the set itself with 3 additional timestamps, -infinity, infinity, and tau empty as the empty timestamp. And I don't want to talk too much about it, but rather get back to our example, because then you will see how this works. For example, we can include the end timestamp infinity if we don't know when this fact will end or this fact is still valid, because Lionel Messi is still playing for Paris Saint-Germain. Furthermore, we can define events that occur once and are valid afterwards. For example, Portugal has won the European Championship in 2016, and this fact will not end. So it occurs once and will be valid afterwards. Therefore, we define the end timestamp to be the empty timestamp. And with this, we know it occurred in 2016 and it will not end. And with this information, we can define temporal knowledge graphs or temporal knowledge graph extensions. And these are based on temporal ontologies. And it's a lot of text, but basically we're just replacing triple structures by quintuple structures. So we keep the head relations and tails, but every time for each edge or each triple, we add some start timestamp and an add timestamp. And we also can define some temporal rules, like for example, regarding the relation winner, which was used by Portugal being the winner of the European Championship. The start timestamp must be a valid timestamp, and the end timestamp will always be empty because winning something will always remain. On the other hand, we can define rules which seem very complex but aren't really complex, because this formula here just states that if a player plays for 2 football clubs Y and Z, then the time spans of so when he played for these clubs need to be disjoint because he can't play for 2 football clubs, excluding national teams at the same time. And a set of such quintuples is then called a temporal knowledge graph. And as you can see, we can always induce a static knowledge graph if we just ignore the additional timestamp metadata. So the facts on the left-hand side, head, relation, tail, induce our static knowledge graph. And actually, temporal knowledge graphs are like the most well-elaborated field of research regarding time-aware knowledge graph extensions, and they are already used in knowledge graph embeddings and relational machine learning. So that's cool and all, and these can be used to solve our previously stated downstream questions, like how often has Messi scored matches against Ronaldo. But we can face other questions as well, like for example, is Lionel Messi happy with his national career, or does Cristiano Ronaldo speak Italian? So as of now, the knowledge graph is not sufficient to answer these questions, but we could add this additional information, which are true facts, but they were not known before. So Argentina won the Copa America, which is the most important tournament in South America in 2021. And Cristiano Ronaldo played in Italy for Juventus Turin from 2018 to 2021. And this information could be useful for these downstream questions. But the main issue is that we have the initial knowledge graph at 1055. And usually downstream tasks are based on some knowledge graph embeddings, and you need to learn them in a very time and resource intensive manner. And if we add some information, so we update the graph at 1115, and this kind of works out, then we somehow need to affect the input to our downstream applications, so the embeddings, and to, well, receive a new embedding for this updated timestamp. And as stated before, learning embeddings is time and resource intensive. So we somehow need to find a solution for incorporating knowledge graph dynamics in downstream tasks. And to do this, we need a formal definition of dynamic knowledge. And we start off with the opposite of dynamic knowledge graphs, because that's a stationary knowledge graph, which aims at modeling knowledge for a fixed timestamp. And we don't care whether we have a static knowledge graph, so only triple structures, or a non-static knowledge graph with some additional metadata. It's just meant to be a model of the domain for a fixed timestamp, and we can't do any changes to this stationary knowledge graph. So that's why you can see the logs here, no access or access denied. Then regarding, to get to the dynamic knowledge graphs, we assume a family of static or non-static ontologies, so conceptualizations for each timestamp in our time set. And for each of these conceptualizations, we can derive the set of all valid stationary knowledge graphs. And by this, we define a dynamic knowledge graph as a mapping. So it's not a graph structure, but a mapping from our time set into the graph structures, so that for each timestamp, the resulting knowledge graph is a valid knowledge graph. Again, as an example, at 10:30, at the beginning of this workshop, maybe you didn't know anything about football, so you would start off with an empty knowledge graph. Then at 10:55, when I started my presentation, you get to know information about Lionel Messi and Cristiano Ronaldo. And at 11:15, I added new facts. So we have 3 images for this dynamic knowledge graph, and each image is a knowledge graph itself, or stationary knowledge graph. So with all of this, we found definitions, well-defined definitions for temporality and dynamics with respect to downstream applications based on graph-based structures, and therefore also a differentiation between staticness and stationarity. Therefore, we replaced the previously mentioned static approaches as the opposite of time awareness, by static and stationary approaches as opposites of temporal and dynamic approaches. And with all of that, we also created a generalized framework, at least for temporal and dynamic extensions, which can be used to, well, standardize existing work in this field, but also facilitate future research in the context of time-aware knowledge graph extensions. As a short overview for the second last slide, I would like to mention that local extensions are globally valid. What do I mean by that? So a local extension for a knowledge graph is the addition of some additional metadata to a local edge. But these additional metadata should be factual because they describe they describe facts themselves. So a start timestamp should be factual for all knowledge graphs. On the other hand, global extensions of a knowledge graph describe the semantic evolution of a graph. And each knowledge graph can be designed for different domains or they can tackle different targets. So most probably, even though some information is theoretically observable at some timestamp, these two knowledge graphs could include them at different timestamps in the future. Now, we find that time awareness is a crucial requirement to, well, implement knowledge graphs, especially in highly flexible and dynamic domains. And it's not just football, but also manufacturing. So we can observe such knowledge graph structures, such dynamic knowledge graph structures, also manufacturing. And this approach is directly applicable as well. And also, because we introduced a common vocabulary for time-aware extensions in general, we also provide for interoperability of graph-based conceptualizations and AI applications, which want to incorporate time awareness as well. And with that, I would like to say thank you. And there's still one thing I'd like to say, or who Sylvester Stallone might like to say, which is raise awareness for time awareness, because if you want to include knowledge graphs in your dynamic domain, then we provide for two generalized definitions, so temporality and dynamics, but there are more aspects to time awareness, and we still need some tools for our time-aware Swiss Army knife, so we need to still extend this in a well-defined and generalized manner. So please keep that in mind when you work with such extensions. And thank you very much.
Thank you very much, Franz. I would like to ask, are there any questions about time-aware knowledge graphs to Franz? Any questions from the audience?
I have one, John.
Yes, please.
Yeah, first of all, Franz, thank you for the talk. Very interesting. I'm not particularly into football, but still I found it interesting. I think indeed, as you mentioned, this is very useful for the work that we are doing. One of the examples from manufacturing that I can think of, and that also relates to John's question to my talk about efficiency. If you look, for instance, at questions that a data scientist could ask about the state of a particular CNC machine. Is it operational or is it non-operational? That's information which is typically not in the data, but where I would have advocated in my talk, you can have an execution model that can derive such information from the data. For instance, a log file that you can parse. And so by parsing that, you get access to the information, whether a particular machine is in a failure state or not. And now, in order to avoid that a data scientist has to do this calculation every time, coming back to John's requirement of it needs to be efficient, the approach that we, of course, then use in Assistant project is to use some federation of different graphs and to store that generated information in a graph database, for instance, in order to make it quickly available for the latter one. So I clearly see a link to what we are doing, and I didn't talk about the evolution part yet. The $1 billion question is, and I think you you refer a little bit to it with your Swiss Army knife. Now, of course, we have our approach, which is incorporated in a lot of research and open source tooling. If we would like to implement this, for instance, how should we proceed? Do you have prototype tooling that, for instance, allows to annotate these relationships? How do you do it?
So these annotation relationships, it's always about, or if we talk about the temporal knowledge graph, so you need, that's like the main point of my talk, that you need to differentiate between temporal knowledge graphs and dynamic knowledge graphs, because in temporal knowledge graphs, it's just stated that you have some kind of memory, so you know when an edge was valid or not. But in dynamic knowledge graphs, we really consider the evolution of a graph.
Yes, and indeed, I was talking about the former.
So the temporality.
Yes.
So temporal knowledge graphs are usually referred to as property graphs, because in property graphs you can just assign any additional edge metadata to well, your triples. And a very common approach for this is called RDF star. And there, I think in Neo4j it's already available to do this. So you can define your temporal ontology, where you can define, I have some start timestamp, I have some end timestamp. Certain relations in my graph can be assigned this additional metadata, but you can also define other temporal metadata, like, for example, when was this information added to my graph? So this is like, because this faces this is something which needs to be considered in dynamic evolutions. When was this information added to the graph? Or very specific time data, like the time span of how long okay, that's still start and end timestamp. So you can always, I think you can always define such answers in start and end timestamps, but somehow or sometimes maybe you need to reconsider that for specific original relations, they need to look different. But if you want to incorporate this, I would look into property graphs, and especially Neo4j, because it's available for them already. So you can just define, okay, I don't only want, I want to have additional entries on top of the triple data. Or another very common approach, and actually most of these property graph approaches are based on that, is reification. So you transform your edges into nodes, and then you add additional metadata to this, which can also be used, but it's not efficient. So that's the main problem of this. So if you want to do it efficiently, that's not the way to go. So you would not rather need to restrict yourself to to very few edge metadata, and then store it like in an SQL manner, to be honest.
Yeah, okay, very interesting. I think we could continue the discussion for 10 minutes, for instance, on why we don't like Neo4j for other reasons related to interoperability, but that would bring us too far today. But yeah, I think definitely it would be good to sit together bilaterally between Teaming AI and Assistant, I think.
Yeah, that would be cool.
Thank you very much, both. I am tempted to ask, you know, if the knowledge graphs can help me also in explaining things, introducing explanations of AI models. But I'll keep this question for the end, and I'll give the floor to Michele for XMANAI presentation to hear about the explanations first. And as you said, the systemic part of knowledge graphs is really deserves a presentation on its own. Thank you, Franz, for the presentation and the insights.
Thank you, John. I'm not opening the camera because I'm half sick at home, so I'm not good to see in this moment. But let me share the screen with the presentation. Let me know if you see it.
Yes, we can see the presentation, and wish you a quick recovery.
Perfect, thank you. And so I'm going to provide, let's say, the the perspective of XMANAI on data models interoperability for AI system in manufacturing. So the title of the presentation is about the XMANAI Foundation for Explainable Interoperable AI. So I'm going to explain this presentation how we are approaching the creation of the models, the sharing of the models, interoperability of models and data inside the project. Just a couple of slides before, let's say, to reintroduce quickly the XMANAI project. So the vision, the starting point for the project, in few words, is that we think that, of course, AI is finding its way in the industry 4.0, mainly in the future industry 5.0. So there is a, let's say, technological insertion of AI inside the industry 5.0. On the other side, the humans are typically a little insight about AI itself and even less how AI works and how decision and prediction are made. So the so-called black box effect. So we don't know sometimes how the some algorithm works. And let's say, speaking about people in the factory, they don't even know what AI it is. So there is a big gap between what AI can do and what is finding to do in factory and the humans in the factory on the other side. So if you don't address properly the lack of explainability, understanding how the AI works and why some results has been created can jeopardize the potentiality of AI. And so with the XMANAI, we want to fill this gap and through explainable AI that can show to human why a specific result has been presented and not another one, what drove towards a solution and not another one. And so the project is going to is delivering a glass box catalog of hybrid and graph AI models. So we want to use models that can become a glass box, not a black box for the human, that can interrogate them and understand that this human envelope which led to a specific result. And on top of these AI models, we are creating as well the explainable AI platform powered by these models that should inspire trust and augment the human cognition about what is happening and solve especially concrete manufacturing problems using these explanation that are value added on of the project that we are trying to carry to the factory. The target users for the platform and the models are on one side data scientists and data engineers, so that are using the platform to understand better how the algorithms are working, and as well as business users, so people that doesn't know anything about technicalities, which are working in manufacturing, in the factory or in the offices, so blue-collar worker, white-collar worker, that will use the explanation to understand better and decide whether or not to trust the AI on that. The consortium is about 15 partners in 7 nations. I'm representing TXT Solution and the coordinator of XMANAI. And just to phrase where we are inside the project, so the XMANAI started in 1st of November 2020, will end in 2024. So we are now at month 25 up to month 42, which is the entire project here. So we are a bit at the half of the project. At this stage, and the reasoning that I'm presenting you later, the status of the project is that we deliver the first version of the integrated platform for the manufacturing, and we have as well a first version of the explainable AI models that has been delivered to end users. And in this month, so we are executing the experimentation with the end user. This is the ongoing process. So we are closing the first iteration. We already started the second iteration of the project that will lead us to month 42, so to the end of the project. The 4 end user in which we are let's say, applying explainability are visible in these slides. Are four large industries and one SMEs. We have Ford, which we are applying explainable AI on the overall production optimization on the plant in Valencia about engines. We are working with the Whirlpool, EMEA in Italy, especially related to the artificial intelligence for product demand planning. So here we are helping the data scientists and business users of Whirlpool into understanding better where the items will be booked and which kind of items will be booked in the business to customer channel, B2C, which is new in the company. So really need a lot of iteration in order to get that good prediction. And trust is very, very important on this, and also the how to understand the explainability will serve also to understand why the algorithm didn't provide a good demand planning, because it's very difficult in this period that there are no years of data behind, like in the B2B channel, but it's a new channel, the B2C. We are applying this also to CNH Industrial, which is AI for process product quality optimization. So here we are looking on the human, on the maintenance of certain parts of the production of tractors in Modena and Italy. And the fourth end user is the SMEs, is Unimetric in the Basque Country, where we are applying the AI for semi-autonomous hybrid measurement planning. So here we are working on the methodology plan, and we are using AI in order to speed up the process of setting up a project of metrology. So which kind of technologies to use, what to measure, which technologies, which is the forecasted error rate that we can understand, etc. So quite a wide application of explainable AI here. What you see in this slides now is the architecture of the platform, and you can see inside also the explainable AI models catalog and the models that I was telling you before. Without going too much into details in the architecture itself, what you see from the bottom up, we start from data and we end up with services. So in the bottom part, we have the data collection and governance services of data with the data handler, which import, export data, and allow the access to data to all the above mentioned layers. We have also data anonymizer and provenance engine that supports the access to data. We have, of course, the storage service scalable. And above, we have data manipulation services with the engine, knowledge graph manager, so everything that helps in order to manipulate the data that are imported, exported in the platform, and especially connected with data that comes from the four end user I mentioned before. The above level, we have the pipeline lifecycle management model services. That's the typical services for pipeline management, modeling, engineering, the model catalog, or everything that relates to this. And in the above layers, we have the execution services that could be with the orchestration engine. The execution can be done in cloud or on premises, depending, of course, on the specificity of the four end users. If you are talking and which kind of data and which policies we are accessing the data and managing them. As you can imagine, talking about real data and real factories, we have several concerns about let's say, the usage of this data and privacy on that. We have also above the visualization engine that provides let's say, the interface to users via PC, but we are also working towards augmented reality visualization for people that are in the factory, in the shop floor, and needs to move and access to the data while in motion, while working on the machineries itself. And of course, on top of this, the security and the sharing service is part of the platform. On this, let's say, quite wide architecture, even if high level at this stage, we have two different elements, modules that are dealing with data model and data interoperability. On this, so for sure, let's say, having high quality data to build upon what you were saying before is a fundamental to create insightful AI pipelines, but as well, it is important to have a common underlying structure and semantic for this data. So the availability of a data model can significantly facilitate and accelerate data science processes. For example, data science can explore, query, understand the available data, train and evaluate machine learning models, and make the whole process less, let's say, error prone. So XMANAI leverages on these data models almost across all the steps of the AI pipelines, sometimes to enhance the respective process and others to provide functionalities that would be otherwise impossible to achieve, or at least the same level of quality. So definitely we use a common data model inside the project. And during data ingestion, which allows the stakeholder that have knowledge over the data, for example, the business users I mentioned in the first slide, to pass this information in a synchronous manner to the team that will be responsible for the data analysis, data scientists, which are the other kind of users that we have in the project. So we use this common data model during, and the semantics stays with the data. So we put the semantics on top of the data, and this facilitates the understanding for the data scientists, even in the first step of exploration and later on. So the goal is to accelerate everyday operation of the data scientist when it comes to exploratory data analysis, like spot anomalies in the data, create meaningful visualization, anticipating transformation, thinking on useful combination of data, and so on. So the data across the AI pipeline are enriched with this semantics, and this is provided to the stakeholders, and so they can understand how they can be handled. So I say this, the possibility to add these semantics together with the data, etc., will allow us to achieve also the data explainability. That's contribute to the overall explainability of the of our AI pipelines. For the model, as we said, we ensure the data is conformal to the common data model, which provide numerous technical advantages. And inside the projects, this allows the implementation of more advanced, let's say, smarter data visualization rules, enhances guarantee data integrity, and significant facilitate the production deployment and end-to-end monitoring of the pipeline by the data engineers inside the project. Moreover, the data manipulation operators in terms of this can be enabled and disabled depending on the data types and the units of the data which has been used. So the same information can be leveraged in the way visualization are configured, in the way feature extraction is performed, and the way the machine learning models are configured. So having this common understanding of the data being used and enforce certain action rules, quantity, and security tests, which are based on commonly agreed data structure. This not only facilitate the operator, but each stakeholder role in the project, and provide also the foundation for being more productive collaboration among the, let's say, what I said before, so the business user, the data scientist, and the data engineers. If we go more in details on how we build the data model methodology, we have the steps that you see in this picture. So we start with a collection. We start with a collection of demonstrator data requirements, which is the starting point of the definition of the data model, taking consideration the demonstrator data examples that we received and the requirements towards the platform itself. So to gather this information, the partners that are responsible for the technological development and deployment of the demonstrator, technological partner team with the demonstrator partners, and they provide template inserting all the data and the explanation that they have and that they will have, referring to the beginning of the project, to share during the project itself. Then we have the collaborative semantic connection. So the partners collaboratively try to define semantics and vocabularies for the manufacturing scenarios. So this exercise was made focusing mainly on the demonstrator scenarios and requirements, since the manufacturing industry scope is wide and is unmanageable to assess all the possibilities. The manufacturing domain study that you see below is a study on the existing model and ontology standards in the manufacturing, which has been performed to understand the different manufacturing domains and their needed intrinsic differences, let's say. The semantic adaptation with the reference takes input from the two previous steps, as you can see in the graph. Is an adaptation and extension of the ontologies collected and elected as the, let's say, most suitable ones for XMANAI. This was made by partners from all pilots domain, trying not to lose at the time we are merging everything together the manufacturing background that for us is very, very important. So I mean, we are not building an explainable AI fully generic platform for everything, but we are creating what will be the reference explainable AI platform for manufacturing. So it's important for us not to lose the focus on that. The data model designer step, let's say, with the semantic information that we collect and define, it became possible for us to start drafting data models which is suitable to cover, let's say, the XMANAI demonstrator domain specificities that we have all over the project. The model lifecycle management you see below, here we created the step rules to guarantee the maintenance of XMANAI data model during its life cycle, which is really very, very important, not only inside the project itself, but also for exploitation purposes after the end of the project. And the last step is the XMANAI graph data model. So finally, in this step, the process is finalized with the definition of the final data model of the project. Of course, as I said before, talking about model lifecycle management, this is in continuous evolution and will be in continuous evolution also after the end of the project. Talking about the interoperability itself, so we are using inside our own models. So the models are created at the end of the pipeline in collaboration with the model engineering engine and executed, and they're using our own format. Standard like ONNX, you see a picture on the right of the approach, if you don't know it, can support cross-library generic formats. So in the project, we didn't use it for time being. We might use it for the future, so we are thinking about using standards like ONNX or other ones. Decision has been not yet made at this stage, so we concentrate for the time being on the let's say on the creation of first version of the platform of the explainable AI models and the first inclusion into the deployment into demonstrators and run of this. As soon as we have this part done, we'll come back to the standards part for interoperability, and we'll as I said, we'll evaluate ONNX or other ones. About let's say the core of the project itself, so the explanation pipelines, explainability concept in general. Again, we are using our own format for it, and actually we did a research around, but we are not aware about the standardization activities specifically driven by explanation or explainability. So if someone else inside the attendees knows something about this, please drop me a message or comment later on, and we can have a look on that. Explainability is quite a new topic on the field, so miss some approaches here. Let's say was all for my presentation. I went quite fast among all this, but my intention was to show a bit how we are dealing with interoperability, how we create the models, the data models, the data, the interoperability. So how we deal with these topics inside the project. If there is any, let's say, any question, I'm here to answer or to pass this to my colleagues on the technical side.
Okay, thank you, Michele. Are there any questions on the XMANAI presentation? I hear a lot of people saying ONNX and OpenML being very good idea, but in the end they don't use it, and this is what makes me have a second thought. But are there any questions from the audience on the XMANAI presentation? Otherwise, for the sake of time, we could move to Vasilis. Thank you very much, Michele, for the
You're welcome.
For the presentation. We will make also the slides available, and we can move to our last presentation for the day. Vasilis Siatras and Mas4AI project to talk about asset administration cells and agents, how you build interoperable agents with the asset administration cell. Vasilis?
Hello. I'm Vasilis. I'm from the Laboratory of Manufacturing Systems. And let me share my screen before I start talking.
Thank you, Vasilis. We can hear you and see you perfect.
Great. And hope you can see my screen as well.
Yes.
Can you? Okay.
Yes.
All right. Let me start. So today in this presentation, we will talk from one of the parts that we focus on Mas4AI, and this is describing agents, and specifically in this presentation we will see the planning agent using the asset administration cell, which is the pillar entity and communication technology within the Industry 4.0. So if we have a quick introduction to the ecosystem of Industry 4.0, mostly in the lower levels, which are the real or physical entities, as we can see here. I don't know if I can change my pointer. Just the physical things, we have the assets. So the assets can be a resource, can be an AGV, can be mostly physical things, but consumable like material, but in a production system. But they can also be software entities, and these software entities, most of the times they are discussed as agents. This is because up to the latest and more modern research and innovation activities, these softwares can can autonomously work within the Industry 4.0 ecosystem and create decisions and have a more advanced and sophisticated behavior. So in other words, an asset is a very general, let's say, notion, and an agent can be considered an asset within a production. Just because it is software doesn't mean that it is not an asset. So as all assets in Industry 4.0, we include the asset administration cell, which is basically a description of the functionalities, the connections, the links, everything you need to know about describing, manifesting, and using an asset within the whole lifespan of the asset. And so we have to do with the agents. And as we said, agents are autonomously functional units, and they work within, most of the times, a multi-agent system. What that means in practice is that one agent most of the time need to cooperate with other agents. Examples being the planning agent needs to cooperate with other resource agents or AGV agents to command the next tasks that they need to perform. So we need to have a description within this framework, because every entity within the Industry 4.0 ecosystem has an asset administration cell, or at least this is what we intend to do. This is no difference for the agents. And if we move into planning and scheduling and how we can describe a planning agent in general, so just a very basic definition for planning, it defines what to do and how. So it's a more of a mid-term to long-term decision-making process for the production, whereas scheduling, on the other hand, is defining when we are going to do it specifically in time and where, resources-wise. So scheduling is more short-term, we could say, because it makes more decisions about the production. A planning agent, as we define it in Mass for AI, is maybe an oversimplification because it doesn't only do planning, it also does scheduling. What it is in practice is that it is a decision-making agent capable of making decisions for industrial operators in supplies, inventory, factory, logistics, scheduling, planning, and so on. So they solve, or we attempt to solve different problems in different fields for different use cases. Now, the needs for creating such a software, first you have to have the production information. By production information, I mean daily workloads, orders, supply, delivery deadlines, all the important things that you need to know about creating a schedule or a plan. Then you need to also have some assets, interaction and connection availability. So what that means is that you need to know when an asset, and when I say asset, I mean a physical asset such as a resource is down, or when we need to, if we are able to perform another task. So there must be at least some kind of interaction with that. And then we have the multi-agent system communication. And because we have multiple agents managing different data and functions, we also need to gain continuous input from these agents so that we are aligned with the latest decisions within also other fields. And so the challenges of that is that if we need to create a planning agent, we need to make it as much as possible interoperable with within the Industry 4.0 system. What that means is that we need to standardize some kind of information and functions within that provided by the agent in a way that you can reuse it in other systems without very much struggle in understanding in deploying the software. The second is that one of the main objectives is that we need to be easily parameterizable within the lower level algorithmic parts, which means that we will create artificial intelligence solution for the planning, or the algorithms running in the lower levels of the planning agent needs to be easily adaptable to different environments without the need of any development of any additional development activities. And then we also need to have an advanced decision making. And this is just because, as I said, planning and scheduling is not a one-dimensional problem. In fact, it is a very difficult problem even for a small portion of cases. So there are multiple planning and scheduling problems, and each of them defines a different level of complexity. And because most of the time this is very hard problems to solve, you need to have very advanced and sophisticated optimization capabilities. And for, of course, a big problem variety. So these are the main challenges. However, we can consider them as opportunities for a new system. And this is an oversimplified graph, but what we try to do in this project for the planning agent specifically, we call it meta agent, and what we mean is that it is a higher level or a more generic way to say that this agent is able to plan different parts of production. Even this is logistics, transportation planning, resources, material planning. So we had a lot of cases that we needed to address. So what we did was that we created a unit which we called planning meta agent, and this unit is as you see here, this tries to say that it's capable of using different AI algorithmic plugins depending on the problem that it's having in order to be able to solve different types of problems. We call that AI toolbox, and what it does actually it is consisted of multiple AI algorithms for scheduling and planning, which each of those are specifically for a type of problem. And because we needed to make that not as much as more interoperable as possible, we included the asset administration cell of the planning agent in order to describe the behavior of the agent, the capabilities of the agent within solving different problems. And this, of course, depends on the toolbox as well, but we needed to have that in a description for the agent. And then we also needed to define within this asset administration cell for this agent the interaction capabilities with other agents and what is the protocol and in interacting and with the other agents. So maybe also a simplified way to show some of the sub-models and the properties included into the planning agent AAS. So we firstly, if we see the key topics, we needed to create an identification for the agent. So once we instance the agent, how other systems can access it, how we can find it, and what is the way to interact with the agent. And then we needed the life cycle of the agent. The life cycle is basically the assignment of different, rather than just the spawning and killing the agent, we also have the assignment of different tasks to the agent. So we needed to find a way to describe the assignments in a way that they would be generic enough to also identify the nature of the problem, which means that what type of scheduling or planning problem it is, give hints on the scheduler, on the agent, on what algorithms should be used, because as we said, this is considered to be, or we try to be a meta agent, which means that it will be able to decide among different algorithms. And then also identify what should be the response to the other, to this call for a scheduling or a planning operation. This brings us to the next, which is communication. We needed to define a framework for interacting with the other agents, and this should be as granular as possible. Just because Mas4AI has this type of agents doesn't mean that there shouldn't be even more. So we need to find a way to standardize somehow the capabilities for interacting with other agents, whoever they might be. And then, of course, we needed to define what are the AI algorithms included within the agent. So in general, what we have here, and we see that we have the optimization toolbox, which is consisted of multiple optimizers. Maybe we call it schedulers or planners. In practice, there are optimization services, and they can give you the capabilities of what problems they can solve, which is actually described within the capabilities sub-model collection. The capabilities, if we move into more detail, they can also split into different, describing, for example, the environment, the objectives, the type of objectives, and then the constraints. We won't jump into that detail, but this is a way of describing that this specific optimizer can give you solution to these type of problems, and capabilities describe the problems. Now we also need to find accessibility, because we have the optimizer, it doesn't mean that the optimizer is within the same software as the planning agent. the planning meta agent. It can be on another, as we will see in the architecture later. File format, of course, parameters for the agent, so the parameterization. And then this is linked actually with the assignment. The assignment is a workload. The workload, of course, is the type of orders that we need to schedule, could be or task specific, and whether the tasks and the nature of the problem corresponds to the capabilities of the optimizer, then the optimizer is a possible choice. So this is a simplified, more high-level description of what the AAS of the planning agent looks like. Now, of course, we need to find a way to carry that information about the production. Let me also see the timing so that I don't lose enough time. So that we need to, of course, we can create different agents, all right? So that doesn't mean that each agent should carry all the information that it requires for scheduling. And because entities such as orders, jobs were not within the asset administration shell ecosystem, let's say, we try to create them as individual assets. So we created the order, the job, the task, and as you see, a multi-layer architecture of assets. These assets are not software, they are not physical assets, but they are assets, information assets that the agent needs. And so that we do not replicate each time that we created an agent or a different problem, we create them as autonomous instances within the factory. And they describe actually the current status of the factory, the also physical entities such as resources, but also planning related entities. So this could be the source of information for the agent. And when we assign something to the agent, we don't need to pass that information, but we just need to reference it and where we can find it on the asset administration shell platform, let's say. So that brings us to how we can integrate it to the Industry 4.0 ecosystem. Of course, as most of the components in Industry 4.0, and technologies, they have multiple layers, and such as the planning agent. It has the business layer, which is basically the reference to the production required, as we previously said. The functional, which is the algorithmic part. Information layer is the input and output required for the different algorithms, because of course it doesn't mean that each algorithm, they need to pass a filtering process before we can pass it to the algorithm. So this is this layer, what it does. Communication layer, of course, because we need the communication with other agents. And then the asset is where the actual planning agent running, what are the resources that are used, the computational resources available for these optimization processes, and so on. The Industry 4.0 ecosystem should look like that. Agents are included in that, interaction with planning agent instances, but also interaction with other assets such as the customer order, which is not, as we said, is an information asset, or another physical asset, which could be a sensor and or maybe an AGV, and we need to find the current status of that. Other agents. So it's more of the description and actually establishing that within the deployment of the agent within the Industry 4.0. Now we will move into the most technical part that this presentation has, and this is the last one. We can see a prototypical deployment just for the planning agent, and we see here, if we take it from the lower left side, because most of the times in a factory it's not everything digitalized, so it can be some things that either are manual, or there is no a way that the agent can command the production to do something, because, for example, it's not an AGV which has these kind of capabilities, and it's kind of another resource that don't have the capability, or it's not integrated with the multi-agent system. So we do need to have some kind of user interaction. For that, we use user interfaces. And for the user interfaces, we are also capable of interacting with the multi-agent system. Janus is actually a multi-agent system framework where you can instance agents of different types. And that is what we did. We are using Janus in order to create an instance of the planning agent. We call it proxy because it's not the actual software running within Janus. And we can use that in order to interact with the actual software, the planning meta agent. So within this framework, if another agent give an action to the planning agent, this action could be that there is requested or required scheduling or rescheduling or planning or replanning operation. That would be passed through a middleware. We can see an example here, but of course you can do it multiple ways. This is what Mas4AI is doing at the moment. And passing that to the planning agent, the specific instance corresponding to that proxy agent, which may be running on a server somewhere, or could be running within Janus as well. It is totally dependent on the case. Then we can actually find all the information that we need for planning that, and those information correspond to this customer or these jobs, tasks that we previously set from an AAS platform. So an AAS platform is where we actually register these AGVs and we upload them so that we can identify where they are and we can download them. So the plan agent would download, filter this information, and decide which is the most possible AI solution, the most suitable AI solution that you should use for this scheduling problem, for this problem in general. And then there's going to be some communication between those two entities, and information will be passed back. And then the planning agent, first of all, it will upload everything that it's needed on the AAS platform, which is where the information for the assets is stored, and will communicate with other agents if so is required. And that is something that is defined within the action that it's sent by the other agent. Now, an important thing in that is the top right, which is where how information is actually stored most of the times is actually stored before Mas4AI in a production. So an ERP doesn't mean that they have the same kind of modeling as to different ERPs. What I'm trying to say is that they have different modeling. So we need to find a connection with that through that in order to create this standardized or more standardized version of describing information in a way that the planner will be able to know exactly where to find what. And this, of course, is customizable for different ERP kinds, but for all the other parts is just as easy as a plug and play for different environments, as long as you create this type of information in the format that is needed. So it's all a matter of mapping in the end. I would like to conclude that what we did on one part, because as I said, Mas4AI is not only this, but we created the planning agent architecture as better as we could in order to be generic. We created the asset administration cell description for that agent and the optimizers on the background. Then we created different assets for storing production information. Either this is an order, customer order, material, supplies, everything that you need to know. And for all the problems or the use cases that we had, then we created some strategy for the integration in the multi-agent system. And just to state that this was maybe the hardest thing to establish and standardize. And then the achievements on that is that in the end, and of course, Mas4AI has another year in front of it, so we are still working on that, and maybe updates will happen. But interoperability is our final goal. Create easy to use AI solutions and standardization of the input and output in a way that other industrial environments and cases can use it and map their problem into the input and output, so that the planning agent is easily deployed, installed, and used in another environment. I will have to close on that point, and I am open for your questions and comments, whatever you actually like.
Thank you, Vasilis, very much. Very, very interesting, right? I think this is a redefinition of the term agent, right, in the context of asset administration cell. Are there any questions to Vasilis? If not, and because we are a little bit, late in time, I would like to thank Vasilis, to thank all of our speakers today. It was really a small but very concise and very practical workshop, and I really appreciated that. And I think we will share the recording to, of course, to other cluster members and to all registered participants. And with your permission, I will share also the PDF slides. So thank you very much for being here, and thank you for your contributions. Paolo, can we stop the recording? Anything you want to say from your side?
No, nothing. Just thanking all you and everybody, because I also think it was a very effective workshop. So I'm
really.
Yeah.
Not some big attendance today with respect to other workshops, but really